Hello, welcome back to MEC 975 Advanced Vibrations. In this video, we are going to continue our discussion of multi-degree of freedom systems. Specifically, we're going to go through the procedure of modal analysis. We'll label this section 1.4.2. In the previous video, we did not label that subsection. If you have not done so, you should label it as 1.4.1 matrix equations. So with that, let's begin. So we're going to assume that we starting with the following equation of motion, mx, this is a matrix, mx double dot plus dx dot plus kx is equal to external forcing, mass matrix, m is the mass matrix, x dot acceleration vector, d is the damping matrix, x dot is the velocity vector, k is the stiffness matrix, x is the displacement vector, f is the external forcing vector. And then we also need some initial conditions. So let's say that x of 0 is equal to u, and x dot of 0 is equal to v. And we're going to make the following assumption. That the damping matrix is proportional, that we have proportional damping in the system, and what this means is that D can be decomposed. Let me rewrite the D. D can be decomposed as D is equal to alpha times m plus, and I'm going to run out of space here. Let me try and move this a little bit over. Sometimes easier to just erase than move. D plus beta k. So basically that D is just proportional to the mass and stiffness matrix as shown here. We're going to go through a worksheet to define when a damping matrix is proportional and when it is non-proportional. In the case of it being proportional, you get nice real normal modes. In the case of non-proportional damping, you end up with complex modes. And I mean in the term, like the mathematical sense of complex, that you have real and imaginary parts. And in that case, you have a couple options of solving. You can either use, you can try and use complex modes, which is much more difficult and doesn't really make a lot of physical sense, or you can do it through state space formulation, which I'll be sending a handout on that at some point as well. Alright, anyway, we are going to assume that we have proportional damping. So if we have proportional damping, the first step in applying modal analysis will be to formulate and solve the eigenvalue problem for the undamped and unforced system. So formulate and solve the eigenvalue problem for the undamped and unforced system. So we're going to ignore the damping matrix and the forcing vector. To do this, we make the following ansatz. And if you haven't heard this word before, the word ansatz is a German word that just means educated guess. It's used quite a lot in mathematics when we are just taking a guess at what the solution is and then plugging it back in to see what happens. So we're going to guess that x of t is equal to e to the minus lambda t times some vector c. You'll often see this written as c times e to the minus lambda t or e to the lambda t, but for proper notation, in fact, the term with the exponential is actually a scalar, and proper notation is to write a scalar multiplied by a vector. Okay, so you plug this into the equations of motion without any forcing, so we can plug this in to mx double dot plus kx is equal to 0, like that, and then this will then give us the following problem, or the following equation. We will get minus lambda squared times m plus k, and let's drop the matrix, the underbars. Actually, we'll keep them for right now, just to be a little consistent, times c is equal to 0. Okay, so the vector, and that's a vector 0. So c is equal to 0. This gives us a trivial solution, which means it is a solution, but it is an uninteresting solution. So what we want is we still want to satisfy this equation, but we don't want c to be equal to 0. So instead, what this implies is that the determinant of minus lambda squared, I'm going to drop the underbars now, m plus k must be equal to 0. The determinant must be equal to 0. This will then lead to what's known as the characteristic equation. Which will have the form of something like an times lambda to the n plus all the way up to some value a1 times lambda plus a0 is equal to 0. From here we solve for lambda. What we'll find is that we have n different solutions. So for lambda n, from there we can find the natural frequency, which is omega n, is equal, actually let's say lambda I. So for lambda, this will lead to lambda I, which leads to omega I being equal to the square root of lambda I. Okay. And I suppose it can be plus or minus square root of lambda I, though we only consider the positive form. So, we call omega I the natural frequency, the ith natural frequency. So omega I is equal to the square root of lambda I, and this is the ith natural frequency. Okay, now that we've found our eigenvalues, or lambdas, the next task is to determine the eigenvectors. So we can say, next, determine eigenvectors. So we want to find CI's. To do this, we are going to substitute in for lambda I into the eigenvalue equation and solve for each eigenvector. So specifically for each lambda I, we're going to substitute into minus lambda I squared times m plus k times ci is equal to 0. And we're going to solve for each ci separately. This will allow us to find all of the normal modes for the system. So a normal mode has both a natural frequency and a mode shape that must be included. If you want to talk about a normal mode, you have to know the natural frequency and the mode shape. Okay, at this point we've now successfully solved the eigenvalue problem. The next step is going to be to mass orthonormalize those mode shapes. And if you're not familiar with the orthogonality principles for normal modes, eigenvectors, eigenvalues, please let me know, and we can go through it during class time, or I can send a handout on it. Okay, so to mass orthonormalize these, we're going to rely on the fact that mode shapes have arbitrary amplitude. In general, they can have arbitrary amplitude. So we're going to specifically choose a specific amplitude. So let's say that phi I is equal to a scalar alpha I, which is different than the alpha used in the proportional damping. Alpha I times vector ci, and this phi I is also a vector. Okay. We want to solve for alpha I using mass orthogonality. So we want to solve for alpha sub I using mass orthogonality. So with the way we set up our eigenvalue problem, the mode shapes are mass orthogonal. They're not orthogonal to each other. They're orthogonal with respect to the mass matrix. So specifically what this means is that we want phi I transpose times m times phi I. We want this to be equal to 1. Okay? Which means that we get alpha I times ci transpose times m times alpha I ci. We want this to be equal to 1. Alpha I is a scalar. We can pull that out. This is then going to give that alpha I squared times phi I transpose times m times phi I is equal to 1, and therefore alpha I is equal to the, plus or minus the square root of 1 divided by phi I times m times phi I. That should be phi I transpose. And in this case, what can happen, or we can choose either positive or negative. Generally, we'll just go with the positive. It doesn't make a difference for any of the math here. So now that we know the alpha i's, we can determine what phi I is. So therefore, what we call the mass orthonormalized mode shapes, and these are phi I. These are our phi I, and in this case, since we know what alpha I is, they're equal to alpha I times Ci. Okay. From here, we can form a mass orthonormalized modal matrix. And this is going to be, we're going to use capital Phi here. And this is a matrix is going to be equal to, and we're going to basically, in every column, we're going to put a mode shape vector. From phi 1 to phi I, all the way up to phi n. And this modal matrix will satisfy the following. I'm not going to write underbars anymore here. But so phi transpose times m times phi, this is equal to the identity matrix. And phi transpose times k times phi, this is equal to a diagonal matrix where the entries are omega I squared. And the symbol here, this just means a diagonal matrix rather than any other kind of matrix. Diagonal matrix where the entries along the diagonal are omega I squared. Okay. I'm going to stop this video here, and then we'll continue in the next video, starting with how to we're defining the modal coordinates and then substituting those into the equations of motion.